Welcome back, everybody. We're up to the very last lesson of Unit 4, Lesson 17. Once again, no new lesson notes, so we'll go right into the examples. So the following function represents the number of hours it takes for 1,000 bacteria, doubling every hour, to reach a population of X in thousands. And here is our function. So H equals log base 2 of X. Okay. Suppose the function d, defined by d of x equals log base 10 of x, represents the number of days it takes 1,000 of another species of bacteria to reach a population of x in thousands. How is this bacteria, or how is this population of bacteria growing? Well, in log base 2 of x, when we were doubling every hour, the base was 2. So in the case of function d, the base is 10. So how is the population of bacteria growing? It's multiplying. Instead of doubling every hour, instead of multiplying by 2 every hour, it's multiplying by 10 every hour. Okay. Graph D, using graphing technology, make two observations about the graph. So we're going to graph log base 10 of x on Desmos. So let's do that. So log base 10 of x. Okay, here is my graph here. If I go down, notice the graph never goes in the negative. Okay, it turns out for a logarithm graph like this, turns out this y-axis here is a vertical asymptote. So the graph will always have positive x values. Okay, there are no negative x values. Okay, so that's a consequence of the y-axis being a vertical asymptote. So that's one observation. I'm going to write that down here. Okay, so the y-axis is a vertical asymptote. Okay, remember we talked about vertical and horizontal asymptotes back in Unit 2, way back in Unit 2. All right, so vertical asymptote meaning it's a vertical line, and notice the graph gets infinitely close, but never actually crosses that vertical line, that y-axis. Okay, and then I see it has an x-intercept at 1, 0. And if we go to the right here, notice it's very slowly increasing. So it's only going to have one x-intercept. So it has an x-intercept at positive 1. So that will be my second observation. Okay, it has an x-intercept, 1 x-intercept at x equals positive 1. Okay. So number 3, use your graph to estimate the values of d of 50. Use your graph to estimate the values of d of 50. So d of 50 and d of 20,000. Okay, so let's do d of 50 first. So I want to know when x equals 50, what is the value? So I need to go to the right here. Okay, so if you're using your computer, if you hold down your mouse and drag it along the graph, we can get as close to 50 as we can. We might even be able to get exactly at 50. So we're going to call that 1.7. We're going to call that 1.7. So at x equals 50, the value of the graph is 1.7. Now, they want us to explain what each value means in that situation. So go back to number 1. It says log base 10 of x represents the number of days it takes, the number of days it takes 1,000 of another species of bacteria to reach a population of x. Okay, so it represents the number of days. So what this is saying is 1.7 is the number of days. So it takes, this is saying that it takes 1.7 days for the population to reach. Now, in this case, it's not going to be to reach 50, it's going to be 50,000. So for the population to reach 50,000. So D of 50 equals 1.7 is saying it takes 1.7 days for the population to reach 50,000. For D of 20,000, okay, this is going to be a different story. So D of 20,000, okay, what that really means is 20,000 thousand. Okay, so 20,000 thousand, that means to get the actual value, since 1,000 has 3 zeros, I need to essentially add 3 zeros to 20,000. So 20,000 thousand, all right, if I add 3 more zeros, okay, 20,000 thousand is really 20 million. So whatever D of 20,000 is going to tell me how long it takes for the population to reach 20 million. Okay, so let's go back to the graph. So we need to get to 20,000. So what I'm going to do is I'm going to go to the wrench, and we're going to change my x-axis settings. We're going to say, let's go from 15,000 to 25,000. So 15,000, 25,000. So 20,000 is going to be right here. So again, if I click on the graph and then hold my mouse and drag it along the graph, I can get really close to 20,000. So we're going to say 4.3. All right, so D of 20,000 is approximately 4.3. So this is saying it takes 4.3 days for the population to reach, okay, and in this case, it's going to be 20 million. So it takes 4.3 days for the population to reach 20 million. Okay. So number 4, estimate or find the population after 5 days. So if I want to find the population after 5 days, okay, since this tells me the number of days, I have to take that log base 10 of x, and I have to set that equal to 5. Okay? So I'm going to take log base 10 of x, and I'm going to set it equal to 5. So when I'm solving an exponential equation, I have to take that and convert it to log form. So in this case, I'm solving a log equation, so I'm going to do the opposite, and I'm going to convert it to exponential form. So my base is 10, Okay, my exponent is 5, and then x goes after the equal sign. So log base 10 of x equals 5 is really saying x equals 10 to the power of 5. Okay, so 10 to the power of 5 is 1 followed by 5 zeros. 1, 2, 3, 4, 5. So what is the population after 5 days? The population is 100,000. After 5 days, the population is 100,000. And all I did was I took log base 10 of x, set it equal to 5, and then convert it to exponential form. Okay? That is it for lesson 17, and that is it for unit 4.